Okay, so that's how to do the chair conformation on with the Newman projection. Okay, so notice that there's two different positions here. There's the ones that are up top, above and below. Then there's these ones kind of sticking out. Okay, I want to talk about those. Okay, so what we see is in the case of this cyclohexane, we have two different locations. And the way to look at it is if you have the cyclohexane is Earth and you draw the axis of the Earth that spins around, all of the hydrogens that are parallel to that axis are axial hydrogens. So this is axial, 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 axial. See how they're all parallel to that axis going through the center of the cyclohexane. And like all good planets, they have an equator on it. So notice that all the ones that go around the outside edge are called equatorial hydrogens. So the ones facing out are equatorial, the ones that are pointing up and down parallel are axial. And the cool thing is that when you draw them, you can see that the axials will turn into equatorials sometimes, and the equatorials will turn into axials. But wait, we'll show you that in a minute. All right, question on the axial. Okay, so there's also another conformer that happens a lot, and it's called the boat. And when we have a boat, we're going to draw our cyclohexane again, two parallel lines right here. If we were to take this compound and tilt this part up, and just that, only that atom moves right there, and then these two atoms rotate, we're going to end up with something that looks a little bit like this. Okay, we're going to have a hydrogen here, and a hydrogen here, hydrogen here, and hydrogen here. Okay. So notice that all we've done is turned it into moved one atom. We have enough freedom to do that. It's still almost 109 degrees. But now we have these two hydrogens up here are butting into each other. We call these flagpole hydrogens because if you put flags on the two ends of the boat, they would be the flags that kind of bump up against each other. What we're also going to see is that these are starting to eclipse each other here. So this is not perfect. It doesn't have, all the angles are 109.5, so there's no ring strain per se, but we do have eclipsed bonds. So it's not as stable as that chair conformation. Okay, so I said we have the boat conformation and we have the chair conformation. Are there other conformations? Well, yes, there are. There are a few. So in this case right here, when we transfer from the chair to the boat, we have to go through a couple different conformations. The first conformation is what we call half chair. See how we've just pulled this up till it's flush. Now notice all of these are now going to eclipse each other, which is why it's a high energy state. In fact, it's the highest energy state on our energy chart, and takes us to our half chair. To relieve some of that energy, it's going to twist, and we call that the twist boat. And that twist boat is not bad. It's not lowest energy chair, but it's not bad. And then we go to the full boat. And the full boat is, we have those two flagpole positions that are buttoning up against each other. That's why it's a slightly higher energy. And then if it keeps going, we can start pulling this end down. It'll go through the twist boat, through the half chair, and back to the other chair. So there's two chair conformations. And it goes back and forth between those by going over each of these energy barriers, okay? So we have chair, and then we have the opposite chair. Question?
How do you know just by looking at the shape, like where the CH2s are?
Where the CH2s are in the shape, like in the cyclohexane, they're all CH2s, right?
Oh, yes.
So they're all CH2s, and so whenever you can either draw it without the hydrogens on it or draw it with the hydrogens on it.
Okay.
And so until we start adding substitutions, there's going to be two hydrogens on every carbon. All right. So now let's see how it changes our structure to have a substitution. Okay. So let's start with something simple. like, let's draw it this way. And so that would be that way and that way. So that way and that way, CH3. Okay. So this is starting out right here. And our methyl group, is it on the equatorial or the axial position? It is equatorial because it's facing out from the axis, which would be straight down the middle. And that hydrogen is parallel with that axis. So we know that that's where it is. So that's a good place for it to be. But let's turn it into the other chair. So to turn it in the other chair, we have to pull this side down and push this side up, which is going to make it look like this. And now the methyl group is going to be down and the hydrogen is going to be over here. Okay. So I didn't rotate the molecule. What I did was I went from the first chair to the second chair. Now, where's that methyl group? That methyl group is in the axial or equatorial. It's in the axial. This always happens. Whatever is on the axial on one form will be on the equatorial on the other. If it was on the equatorial on one form, it's going to be the axial on the other. They always switch positions. All 6 hydrogens that are axial become 6 equatorial hydrogens. Okay, so that's a good way to think about this. Now, which one's more stable? Okay, let me draw this one right here. And I'm going to draw it this way with a carbon and a hydrogen and a hydrogen and a hydrogen, and then hydrogen and hydrogen. Okay. So if I draw the same one, this one over here, we have hydrogen, hydrogen, hydrogen on our equatorial. So in the case of this one, our methyl group is equatorial and it is not near anything else. But if we look at the methyl group on this one here, these hydrogens are starting to butt up to the other axial hydrogens, the hydrogens in the other axial position. Okay, so that means there's steric demand here. So that is going to be less stable because they're butting up against each other. There's electron-electron repulsion, and therefore it's going to want to favor the other group. It's going to want to favor being in this position. So can we kind of quantify that to figure out, you know, how much sterics really is a factor? Well, if we look at this table here, if we had only hydrogens, just regular old cyclohexane, the amount of time it's going to spend in chair 1 or the first chair and then the opposite chair is 1 to 1 because there's no difference between the energies. They are perfectly, you know, staggered configuration, 109.5 degrees. So for every one that spins here, it's going to spend another one here. But just by putting the methyl group on there, for every 19 molecules, 18 of them are going to have that methyl group at the equatorial position. Okay, so that's almost 20 to 1, right? By bumping it up to an ethyl group here, it's going to be 21 for every one molecule. So that's over 20 to 1. So it's going to be there 95% of the time, right? So if we go up to an isopropyl group, which is even bigger, 35 to 1. Okay, so that's like 97% of the time. And then if we go up to their biggest substituent, we have opiate substituent, we have is the T-butyl group, 4,880 to 1. So it's basically in that position 99.99% of the time. Okay, so now some other groups that aren't as big but have some kind of steric demand can actually, you know, have a little bit of shift. But notice the alkyl groups have a much bigger shift than the other groups we have. Okay, so questions on that? So what this means is if you have a big substituent, it's going to try to be in the axial, no, not going to try to be in the, it's going to try to be in the equatorial position as much of the time as possible. Okay, so that being said, let's see. What happens if you put 2 on there? Okay, so I'm going to draw another cyclohexane. This one right here, CH3, H, CH3, H. Okay. Just randomly put 2 methyl groups on there. These 2 methyl groups are in the axial or equatorial position. These are in the equatorial position. So they're probably pretty happy here right now. But let's flip this ring, since we know we have some equilibrium flipping back and forth. So we're going to pull this down, which means this is going to rotate up. We're going to pull this up, which means this methyl group's also going to rotate up. So when we redraw it, the methyl group is here. Notice the position between this hydrogen and methyl group stays the same. All it does is go tilt. Okay, it just goes tilt. It doesn't go anywhere else. And this one right here tilted up too. So this one, CH3, is up here, and this hydrogen is sticking out. So now our hydrogens that were axial position are now equatorial. And now our methyl groups that were equatorial are now axial. Which one's more stable? The one where both groups are equatorial, because they have the 2 alkyl groups are in the equatorial position. Okay. But what if we had a different one? So this is the favored one, lowest energy, more favored, right? So what if we drew these same ones, and instead of putting them where they are on a curved line, right here, we're going to leave this methyl group exactly where it was, but we're going to switch this one. Okay, so in this position, we have 1 methyl group in an axial position. That's this one down here. And 1 in the equatorial position. Let's swap it. Let's flip it. And when we flip it, we see that, yes, it takes practice to flip these things. Let's see, the methyl group is going to stick out here. And the hydrogen is going to stick up here. This one, the methyl group is going to stick up here. And the hydrogen is going to be here. Okay, so how many methyl groups do we have axial? 1. How many methyl groups do we have equatorial? 1. So is there a big energy difference between these 2 structures on the bottom? No, they both have the best they can do is put 1 axial group, 1 equatorial group. And when it flips back and forth, the axial turns into equatorial, the equatorial turns into axial. Okay, do we see that those are now equal in energy? They have the same potential energy. But what if we change one of those methyl groups to something else? Okay, let's look at and let's do let's do a T-butyl group. Actually, I'm going to draw it as in stick figure so you can see how big it is. Then a hydrogen here, and then a hydrogen here, and a methyl group there. Okay, is that T-butyl group in an equatorial position? Notice the hydrogen is pointing up, so that means the equatorial position is where the T-butyl group is. So the methyl group is also in the equatorial position. Okay, so if we were to flip this, we would have them both in a axial position right here. So which of these is favored in an equilibrium? Left or right? The left one, because these are both in that equatorial position. So let's do that same thing we did before, where we had this, and let's put the T-butyl group here again, but let's move the methyl group. Let's put the methyl group in that axial position. Okay. So now in this one, we have 1 group in an equatorial position and 1 group in an axial position. position, but it still can move and has equilibrium. And if we flip that over, we now have this methyl group. Hey, finally, we have that methyl group in the equatorial position. But now we have this T-butyl group in the axial position. Is there a favorite location for this structure? Which side is going to be more stable, have lower energy? The one on the left, right? The one, the largest group on the equatorial position is going to be lowest in energy. All right, questions about that? Okay, so that's what we're going to learn about cyclohexanes. We're going to use cyclohexanes as an example for lots of things because we don't have to worry about bending and twisting around. We know it's going to have low energy, low strain, and so we're going to see it happen a little bit more like that. All right, so next thing we're going to move on to finish out this chapter is reactions of alkanes. This is our first reactions. We're actually doing chemistry now. Yay. Not really. But so hydrocarbons don't do much. So we can burn them. So we can do CH4 plus 2 equivalents of oxygen goes to, let's see, CO2 plus 2 equivalents of water. Okay, so we can burn that. So that turns it into an inorganic compound, and therefore we don't care as organic chemists about this very much. The only reason we're going to use combustion here is determine the energy that something has. We're going to use combustion, the heat of combustion, to measure energy. Okay. Now, the other thing that they do, and I alluded to this when we did our substitution reactions, is what we call halogen, radical halogen substitution. So we can take something like this group here, react it with bromine, Br2, and it's in the presence of heat or light. This is H nu for light. And it'll substitute one of the hydrogens for a bromine. There it is. For a bromine and produce HBr. Okay. We're actually going to go over this mechanism in chapter 10, so we don't have to worry about that just yet. But it's a substitution reaction. So that's one of the few things we can do. Okay, so those are the two reactions we have for alkanes. Okay, how do we get to alkanes? Well, we typically synthesize alkanes from alkenes and alkynes. So if we have an alkene or an alkyne, we can do what's called a reduction. We're going to add hydrogen across a double bond. So let's draw an alkene and draw just hydrogens here. Okay, and I'm going to draw an alkyne, and it has 2 hydrogens on it right here. And so if we take a catalyst and take hydrogen, elemental diatomic hydrogen, sorry, with a catalyst of platinum, PT, palladium, PD, or nickel, and I, usually under pressure with heat, we can add that hydrogen across that double bond. That's one of our other things. We did a substitution reaction. This is our addition reaction. And what that's going to look like is we're going to have all the hydrogens and carbons we already had. Oops, hydrogen, 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 hydrogen. But we've added 2 new hydrogens and 2 new sigma bonds, right? We got rid of our pi bond and got 2 new sigma bonds. Okay, we call this a saturated hydrocarbon because you can add no more hydrogen to it. Okay, now it turns out you can do the same thing with acetylene, except it's a little different. If we go and add 1 equivalent of hydrogen across it, we get an alkyne. No, we react that alkyne, we get an alkene. And here's our originals. And here's the 2 we just added. Okay, but as we know, alkenes react with that same catalyst system. This is hydrogen with platinum, palladium, palladium, and nickel. We can do it again with another equivalent of hydrogen. And so we're going to end up with our hydrogen, 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 hydrogen. And of course, we still have those original carbons and hydrogens from the original molecule. Okay, so this is called reduction. It's our third reaction we have. And we use this catalyst system of hydrogen with palladium and platinum, usually with heat. Okay, we're going to do a little bit more on this in chapter 7 as well. Okay, questions on that? So when we were doing our Lewis dot structures, sometimes you're like, okay, well, is there a double bond here? What's happening? We actually have a way for calculating the degree of unsaturation. So if saturated means you have hydrogens or something bonded to all of your carbons, unsaturation means you have at least a lack of 2 hydrogens. So every double bond you can have 2 hydrogens go on it. Okay? So that could be a double bond. That could be a carbonyl. That could be a triple bond. That would give an unsaturation because we can add hydrogen across it. Or it can actually be a ring. When we had a linear hydrocarbon, it had 2 hydrogens at the end. If we took those 2 hydrogens off and made a carbon-carbon bond, that gives us another degree of unsaturation. So when we think of degrees of unsaturation, we want to think about double bonds, triple bonds, and rings, or any combination thereof. Okay, so what we have is we have a way to calculate that. And so we have this generalized formula for calculating that. But a saturated alkane, by the way, here's an equation for you. A saturated alkane is equal to CnH2n plus 2. Okay. Which means for however many carbons you have, you should have twice the number of hydrogens plus 2. So that's saturated hydrocarbon. Unsaturated hydrocarbons have at least 2 of these hydrogens missing. Okay, and so we have a way to figure out how many degrees of unsaturation we have. So let's calculate the degree of unsaturation of an unknown compound. Okay, so let's say we have let's see, C4H6. Okay, so I'm going to do the calculation first, and we're trying to figure out what structures are possible here. Okay, so if I do the calculation first, let's figure out how to do the calculation. So if we're using this in a calculation, we have to have 2n, where n is the number of carbons, plus 2 minus 2x. X is the degree of unsaturation. And that's going to be equal to the number of hydrogens you find in your empirical formula, which in this case is 6. Okay, so we have 4 carbons. So 2 times 4 is 8. Plus 2, well, let's just do 2 times 4 plus 2 minus 2x is equal to 6. So that makes this number right here 10, right? So 10 minus 2x is equal to 6. Now, I don't like that x being negative, so what I'm going to do is I'm going to add 2x to both sides. So we have 10, the 2x's will cancel out on this side, is equal to 6 plus 2x. Now I'm going to subtract 6 from both sides. And that way we're going to have that, let's see, 4 is equal to 2x. And now if I divide by 2, I get x. Our x is equal to 2. Okay, so if x is equal to 2, that means we have 2 degrees of unsaturation. That means we have to have 2 double bonds, 2 rings, or a ring and a double bond. Okay, so what would that look like? Let's see, 2 double bonds, that's pretty easy. Oh, let's see, a ring. Well, we only have 4 carbons and a double bond. Ooh, we have to have 2 rings. Okay. So starting out with knowing what your degree of saturation is tells you how many double bonds, rings, or combination thereof you have to have. All 3 of these are valid structures for that empirical formula and that degree of unsaturation. Okay, do you want me to do the degree of unsaturation calculation one more time? Anybody? Anybody? Bueller? Bueller? The equation. Oh, it's this right here. And so the last number is going to be the number of hydrogens in your empirical formula. And the N is whatever, however many carbons you have. And X is what you're solving for. Okay.
The twos are part of the equation that's not specific to this question.
No, the twos are always part of the equation. Yes, yes. Because the hydrogens come in twos. And so the +2 right here, this is the saturated, this is NH2N +2 for a saturated hydrocarbon. That's where that comes from. The 2N +2 comes from a saturated hydrocarbon. The -2X is the degree of unsaturation. So that's where figuring out where the X is. So that's why the equation has those twos in there. Okay? Okay. So if we do that, that's great if we only have carbon and hydrogen. But what if we have another element? If we have another element, then we have to think about how many times each of them bond. Okay? So because oxygen only bonds twice, we ignore it. Okay? So we don't care if there's an oxygen in the system because we ignore it. Okay? Now, we do have to count halogens, but halogens bond to carbon once. So we can treat them like hydrogens, right? They're in the, you know, the hydrogen is in that same row there with all the halogens. So we can count every single halogen as a hydrogen in our equation, okay? Now, nitrogen only bonds 3 times. So we actually have to take away one of the hydrogens when we do nitrogen, okay? So let me do an example of that where we test your metal, okay? I'm gonna do one with a halogen first and then one with a nitrogen in it. So let's do C7H11, Br, and then I'm gonna do CN, C5H7N, okay? So this one right here, so because halogens count as hydrogens, our N for our hydrogen level at the end of the equation is 11 plus 1 is 12. So we have our 2N plus 2 minus 2X is equal to 12. Okay, so we're going to plug in our 7 here for this. So that's 14 plus 2 minus 2X is equal to 12. So that's 16 minus 2X is equal to 12, which is, let's see, 16. I'm going to add plus 2X to both sides is equal to 12 plus 2X. So now I'm going to subtract 12 from both sides. So that gives us 4 is equal to 2X, which makes X equal to 2. So that means we have 2 double bonds, a ring and a double bond, or 2 rings in this compound. Okay? So now let's do the nitrogen. We're going to do that, and we're going to figure out what this number is here. Okay, so we had 7 hydrogens here. We have 1 nitrogen here, but we have to subtract it there, which means the number at the end of our equation is now 6. Okay, the number in the end of our equation is now 6. So let's do that calculation again. 2n, so 2 times 7, 7 plus 2 minus 2x is equal to 7 minus 1 for the nitrogen, 6. Okay, now this is going to be 14 plus 2 minus 2x is equal to 6. That's 16 minus 2x is equal to 6, which is 10 is equal to 2x. Sorry, I skipped a step there, but so that means that divide both sides. Oh, is that right? Yeah, yeah. Divide both sides by 2, which means we have 5 degrees of unsaturation.
As the comment up there.
Oh, sorry. Wait, why aren't there 2 times 6? Oh. N is equal to 2 times 6.
I think they meant 2 times 5.
2 times 5? Oh, right here? I'm sorry, you're right. Gosh. I filled in the wrong thing. You're right, it is 5. Yeah, the N is 5 right here. I'm sorry, I put the number of electrons in instead. So that's 10. So that's 12. So that's 6, which means our degree of unsaturation is equal to 3. So we have 3 double bonds, 2 double bonds in a ring, 3 rings, it could be any of those. So the idea here is that, yeah, their hydrogens here are going to be -1 because of the nitrogen. The hydrogens here are going to be +1 because of the halogen. Okay. And the N is the number of carbons. Thank you at home. Yes. And for you for noticing. Okay, so that's degree of saturation. We're going to have that on the quiz on Wednesday. Just so you know. Okay, so let's move on to chapter 5. Okay, but before we do, let's go ahead and take roll for those of us in person. Okay. So now we're going to talk a little bit more about stereochemistry. I already introduced stereochemistry when we were talking about cis and trans. We said that we had stereochemistry when some group is fixed in space, okay? And we had the difference between them being on the same side of the double bond or being on opposite sides of the double bond. And so that gave us it fixed in space because we don't have free rotation around that double bond. So, but that's not the only kind of fixed in space stuff we have. We also have stuff with sp3 hybridized carbons, and we're gonna talk about that specifically today. Now, the cool thing is that in a lot of our pharmaceuticals, about 61% of all pharmaceuticals have some chirality to them, have some stereochemical aspect to it, and usually one stereoisomer is better than the other. So our body can recognize the difference between different stereoisomers, different fixed in space. Even though every other bond is exactly the same, 2 groups have been swapped in space, and that makes them different. The cool thing is that our body can actually determine the difference here. If you have a compound that you can extract from caraway seeds, it's called carvone. It's got a nice earthy tone to it, okay? And if you take 1 carbon and swap the carbon with this hydrogen, it now smells like spearmint, and it's made by a different plant. Okay, one only makes one only makes the other. They're identical except for that hydrogen and that carbon being swapped in space. Okay, that's stereochemistry. That's why it's important. Okay, so let's talk about isomers first. So we already talked about isomers, and we saw that we had constitutional isomers, right? Where if you move a methyl group 1 group over, it's a different compound, okay? So they're gonna have different IUPAC names, different properties. They could have even different functional groups. You can take an alcohol or carbonyl and it'll have a different functional group. And so we have that, and then they can also have different physical properties, and they should have different reactivity. Stereoisomers, on the other hand, differ only in the way the atoms are arranged in space, okay? Now, they're going to have the identical names except for the prefix. For a cis-trans isomerization, we'll have cis and trans. For a sp3 hybridized stereoisomer, you will have R and S, and I'll explain those as we go through today. They will always have the same functional group, and they only differ in that 3-dimensional configuration. Now, the cis and trans actually have different boiling points and melting points, but the stereoisomer sp3 hybridized stereoisomers do not. They have identical boiling points. Okay, so let's talk about the different types of stereoisomers. So we have stereoisomers, and we have 2 basic kinds. Okay, the first one is what we call geometric, and that's that cis and trans. That's easy to see that they're opposite each other on that, or they're the same on that. So they're fairly easy to identify that way, and that's what we call our geometric isomers. And again, they're differentiated by their names, cis and trans. However, in the case of our sp3 hybridized, we can't tell the difference except by a certain optical method, which we'll talk about later. So we call them optical isomers. And the only difference between them is one atom has been, two atoms have been swapped in space. And in this one right here, this hydroxide and this OH have been flipped in two different locations. And it's only that that changes it from one to the other. And so they have different names, okay? And we're gonna know that these pairs of the two isomers that look like each other but are different are called pairs of enantiomers. So let's look at this one and say, okay, so in this case here, we've taken this methyl group and moved it over a carbon. So is this an optical or a geometric or a constitutional isomer? Anybody? Bueller? So we've actually changed the structure. We've moved a bond. So if we've moved a bond, we have a constitutional isomer. Okay. Now over here, so we've moved this bond from this carbon. We've moved a hydrogen over here. So we've moved two atoms. Okay. Over here, we have all the atoms are bonded to exactly the same carbons. We did not move any carbon-carbon bonds. We did not move any carbon-hydrogen bonds. But the hydrogen is sticking out on this one. The methyl group is sticking out on that one. That's a stereoisomer. The only difference, all the connections are exactly the same, but two are in the opposite locations. Bonded to the same carbons, opposite locations. Okay, so that gives us our stereoisomers. Okay, so how can we tell the difference between our stereoisomers? Well, the first thing we need to think about is we have a name for it. Okay, we call them chiral. Okay, there's a lot of different names. I'll show you a list of names on the next slide, but what I want to talk to you about is chiral comes from the Latin for hand. And they were saying, okay, so you have a hand and you can do a mirror image of your hand and it looks the same, right? But if you try to lay them on top of each other in the same orientation, they don't superimpose. So if you have something that looks like the mirror image but cannot be superimposed, it's chiral. It has handedness, okay? So that's the definition of chiral, and that's what we're going to start to look for. So we need to start thinking about mirrors and ways in which things overlap. So the first way we can look at that is, okay, so these look like they could, if you took this mirror image of the ear and tried to rotate it around, it'll never fit on top of the other ear. You know, it'll be on like a top to top, but if you tried to put it in the same orientation, they wouldn't overlap. Same happens when you have a car, because you would have it, the steering wheel moves from the left side of the car to the right side of the car. So that would be different. But if the mirror image does completely superimpose, like this fork here, you can take those forks and stack them up and they are perfectly aligned. That means it's not chiral. We have a word for that, it's achiral, all one word. So achiral means not chiral. Okay. So we have chiral objects, which are things that are mirror images and non-superimposable. And we have achiral objects, which are just not chiral objects, which are most objects. So let's see an example of an achiral molecule to get us started. Let's do water right here. And when we're drawing these things, we're going to draw a mirror. And then we're going to basically make the mirror image. So I'm going to start with that hydrogen, draw this oxygen over here, draw this hydrogen here. Okay. So I've made the mirror image of it starting from the center out and the center this way. And if I take this, I can actually plop it right down next to here, move it over, and it perfectly superimposes with the other water. Okay. So let's try something more organic-like here. And come on. And we're going to do, I'm going to do bromine up here. I'm going to do, this is my heavy wedge. So this is my chlorine. This is my hydrogen, and this is my other hydrogen. Okay. So we're going to draw our mirror and make its mirror image. So we're going to start here. And so it's going to be chlorine with a heavy wedge. Okay. Hydrogen with a dashed wedge, followed by the bromine. and then the hydrogen over here. Okay, great. So we have a mirror image, but is it superimposable? Well, they look pretty close, but what I'm going to do to convince you that this is, I'm going to rotate this hydrogen to where the chlorine, to only 60 degrees. I'm going to rotate it 60 degrees and redraw it. So here's redrawn with 60 degrees. So the chlorine comes out here and this hydrogen goes back. So we have dash, dash, dash hydrogen, and the chlorine comes out here. So it's out on the left side first, and now it's out on the right side. So is that superimposable with the other structure? The hydrogens line up, the bromine lines up, the chlorine line up, everything lines up. So this is not a chiral compound. It is an achiral compound because it has a superimposable mirror image. If the mirror images can be laid on top of each other, they are not chiral. Yes.
So if the two hydrogens were like different things, like one of those is like a bromine, this would be chiral, but you can't rotate that, right?
Technically, there's another rule to chirality, which we'll get to on the next slide. Okay. What we want you to look for is most of the time when we talk about chiral compounds, they have 4 bonds. Because if it just had the 2 things on there, you would be able to flip it over and around. It would just take more rotate. It would take more moving, but you can always do it. So even if you had 2 different things on oxygen, it would never be a chiral compound. Okay, so let's look at this. And I have an interesting way to look at this. And my first rule of chiral compounds is, are there 4 different things bonded to carbon? If there are 4 different things bonded to that carbon, that might be chiral. So let's look at that. And so in the case of this, we have an ethyl group here and a methyl group here, an oxygen here, and a hydrogen here. So we have 4 different things. So it might be chiral. Okay. And we've already drawn the mirror plane. And so this is the mirror. So we have the methyl groups on here and the OH is there and the ethyl groups there. Now, if we were to take this and rotate it around and try to get them to line up, the oxygens would line up, the hydrogens would line up, the center carbons would line up. But look what happened. The methyl group and the ethyl group are not superimposable. That means that we've taken the methyl and ethyl group and switched their positions in space without ever breaking a bond. Okay, so that means that this is the other isomer. Okay, so in this case here, these are stereoisomers of each other. Okay, the compound and its mirror image, and that pair is called a pair of enantiomers. Okay, so enantiomers always come in pairs, and they all look exactly alike. They have the exact same name except for R and S. Okay, so that being said, let's look for ways to look for what we call asymmetric centers. Here's all the names that it could be called: chiral, stereo center, chiral carbon, stereogenic. I like chiral carbon. I like, let's see, what other ones I like. Stereo center. These all mean the same thing. If you're looking at stereochemistry, you're looking at stereo centers or chirality. So the first rule is that you have to have 4 different things on there. The second rule is if you have a mirror image, it cannot be superimposable. Okay, so are there ways to figure out that by just looking at a compound? Is this carbon here a chiral carbon? Don't forget to add your hydrogen. That's a chiral carbon. It's got a methyl group, a propyl group, a bromine, and a hydrogen. 4 groups. It's chiral. We can see that. We don't know which isomer it is, but we know it's chiral. What about that? Is that a chiral center? Draw the hydrogen. No, because it has two methyl groups. They're the same. So that's not a chiral center. What about that one there? Don't forget your hydrogen. And so you have an ethyl group, an isopropyl group, an OH, and a hydrogen. So we have a chiral center. Yay. We know how to identify chiral centers. Okay, so let's say that. So now we have a chiral center. We have it, one isomer of it. And now when we draw the mirror image of it, we want to have it be so it's non-superimposable. So in the case of with the ethyl group and the methyl group, when we drew the mirror image here, we knew that if we rotated around, the methyl and the ethyl would overlap with each other, and all the others would align. The bromine, the carbon, and the hydrogen were okay. They were not going to do. But if we change any one of those groups so that they match, we go back to an achiral material. Okay. So anytime you see two of the same group on that carbon, it is not a chiral carbon. All right. So, but there's one other sneaky thing that can blow apart your chirality, and that's a mirror plane. Okay, we're going to see this, especially when you have two stereocenters. If you can find a mirror plane in it, it turns it into an achiral material. So what do I mean by mirror plane? Well, in this case right here, we have the mirror going through three of the atoms here, and we have a methyl group on each side. The methyl group is mirrored on the other side. The methyl group is mirrored on the first side. Therefore, it is an achiral molecule because of that mirroring. But let's switch that methyl group with an ethyl right here. So now we have an ethyl on this side, a methyl on this side, and then these are all in the plane. So this is a chiral molecule. We have a plane. We do not have a plane of symmetry. We have a plane there, but we have different things on both sides of that plane. Therefore, we do not have symmetry. Therefore, we have an asymmetric center or a stereo center. All right. How confident are you on your naming things? I mean, finding stereo centers. Okay. All right. Let me give you a couple more rules to help you identify stereo centers. Always look at sp3 hybridized carbons. There must be four things bonded to it. Four things bonded to it. Okay. They must have four different things bonded to it. So if you see a CH3, a CH2, ignore it. There's no way it can be a stereo center. Now you have to make sure that everything is different though. So for example, if we do C, Br, Cl, I, and F, we know immediately that that carbon is chiral because we have four different, obviously different groups on it. But when, yes?
What if you had a carbon bonded to like isopropyl and a propyl? Would that, like, would you consider the isopropyl?
Those are different.
It would still be.
So for example, yeah, actually that's going to be, that's a really good one. Right there, isopropyl and a propyl, those are different groups because if you look at the connection here, this is a CH2, this is a CH with two carbons on it.
Hmm.
So they're different, so it is chiral. Yes. Actually, that was a mixed example anyway.
Oh.
So thank you. All right, all right, quick quiz. All right, is number one chiral or not? Yes or no? No, because it has three hydrogens on it, so it's a no. That's no. Okay. Let's see. Oops. All right, let's look at number two. Is number two? No, it's got three hydrogens on it. We don't even have to look very quickly, do we? Okay, question here. Okay, no, number two. Okay, all right, they're answering the question. That's what it is. Number three. Don't be tricked. Draw your hydrogen in the first time you're doing these. Hydrogen. So we have a nitrogen, a carbon, and then we have a double bonded carbon and a hydrogen. So it has carbon, but that carbon's a different type of carbon. So those are four different things. So that's a big yes. Okay, so what's the next one? Number four. Okay, let's look at this. We have a carbon with a double bond, a carbon with a double bond, a carbon with a double bond and an oxygen, a carbon with a double bond and an oxygen. Oh, wait, hold it. They're different though. On one of them, it's double bonded to a carbon, and one of them, it's double bonded to an oxygen. So these are different carbons. We have an OH and then another different kind of carbon over here. So that's 4 kinds of carbons. So 4 is a chiral center. All right, are we getting the hang of this? All right, let's continue on. Let's see, 5 is in unison now. No, okay, no. Okay, 6, ooh, so 1 kind of carbon, 1 kind of carbon, 3rd kind of carbon, and an oxygen, yeah, 6 is good. 7, ooh, that might be hard. Let's start counting again. Don't forget our hydrogen. The carbon with an oxygen on it, a CH2, and then this carbon has 4 carbon bonds. So those are all different, right? So that one's a plus, a yes. 8, okay? You can do this really fast. Draw your hydrogens on here. It's got 2 hydrogens on it. Is it chiral? No. So what we're looking for is those 4 different things. And let's look at number 9. Number 9. Let's see. Let's get rid of these here. Okay, let's look at what we have. We have a carbon with an oxygen on it over here, a CH2 over here, a CHN over here, and a hydrogen. That's 4 different things. So we have our chiral. All right, so now we have a really good job at isolating our carbons. Okay, the rules are sp3 hybridized, 4 different things, and you're going to have 2 isomers, the stereoisomers, which are going to be enantiomers. Okay, questions on that? Okay, so let's figure out how to draw the enantiomers. I already kind of alluded to it, and the idea is that you can draw any one that you start with and then be able to draw its enantiomer. So for this example here, we have this, and so I'm going to put the OH up here. I'm going to put that one there, this one here, this one here. Oh, we've got to have another hydrogen. So I'm going to have to draw some stereochemistry, and we do have to do it out here, CH3. Okay, so the first step is you must draw it 3-dimensionally with wedges and sticks, okay? When you draw it with wedges and sticks, that gives you a starting point, okay? Then all you have to do is draw your imaginary mirror and then start drawing it from the mirror out. So the first thing we see is a CH3, and that's on a wedge, solid wedge. The next thing we see is our hydrogen, that's on a dashed wedge. Next thing we see is our OH, that's on no wedge. And then we have our stick. Okay, so any isomer you start with is okay. Draw your mirror image of it, and now you have both enantiomers. Okay, now because we have 4 different groups on here, it will be non-superimposable. Okay. All right, so what about in rings? Can we have stereogenic centers in rings? Rings become problematic because number 1, they could have a mirror plane in them. Number 2, you have to know what different groups are. So let's look at this first one here. Let's see, it kind of looks like it's going to be a stereocenter, but let's double check. So let's see, the hydrogen and the methyl group are definitely different. Then we have a CH2 and a CH2. Are those different so far? No. So let's go out one more. CH2 and CH2. Are they different yet? No. In fact, if we keep going around the ring, we're going to end up with the same thing on both sides. Okay, so that means it's not going to be a chiral center. And on top of that, if this methyl group was coming out at us and this hydrogen was going back in it, we could actually make a plane right through the middle of here, and this half of the molecule looks exactly like this half of the molecule. So it has a mirror plane in it, a plane of symmetry in it, and it doesn't have 4 different things. But all you have to do to make sure it's chiral is to change something on one side or the other. Notice if we draw a line here, we have a double bond on the top and a single bond on the bottom. So they're not the same, right? So let's go around and do that same thing we did before, and we're going to do it here. So we have these two are different right here. We have, this is our stereocenter. This is a this is a sp2 hybridized carbon. This is an sp3 hybridized carbon. They're different carbons. We have a stereocenter. And if we try to draw that same mirror plane, we have a double bond and a single bond. So we know we have our system down. Okay, so now we get to the part where what's the difference between R and S, okay? So we have to learn our labeling system to control this. And so we have 4 rules. We only use 3 of them most of the time, but we have a 4th rule on how to label your enantiomers by their R and S name. Okay. So the first thing we do is we look at our numbers, our atoms, and we figure out their priority by their atomic number, not mass, atomic number. So if we drew something like this, and I guess I had to draw stereochemistry here. That was fluorine, chlorine, bromine, and iodine. Okay, which of those has the highest priority? Okay, iodine's the highest number at 53, so we're going to call that priority number 1. Bromine's next, so this would be number 2. Chlorine would be 3, and fluorine would be 4. Okay, so that means that hydrogen's almost always 4 because it's the lowest number. So that's the first thing we do. Okay. If you have the same atomic number, you keep moving on until there is something different. So what that looks like is like with this one, HOH, right? So if we're starting at our stereocenter here, oops, right here, we have an H and an OH, so those are done. And we have a carbon and a carbon. Okay, so how can we differentiate those 2 carbons? Well, if we look at this carbon here, what's attached to it? So this carbon has a hydrogen, and a hydrogen attached to it. Okay, this carbon here has a hydrogen, and a carbon. The one with the carbon has a higher priority atom attached to it, therefore it is the higher priority. So you keep going out until there's a difference. These chains could be 4 and 5 carbons long. Until you got to the end, you don't know which is the one. So that makes this the higher priority. So oxygen is higher than carbon, so that's going to be 1. The carbon bonded to the other carbon, that's going to be 2. This other carbon is going to be 3, and our hydrogen is going to be 4. Okay, so that's rule number 2, atomic number. And then you keep going out if it's the same number until there is a difference. And then the one with the higher atomic number atom attached to it is the one that wins. But what about double bonds? How do we do that? Well, with double bonds, you can actually do something like this. Let's see, we have C, double bond C, H, Br, and there. Okay, so we have an ethyl group and an ethylene group here. We got that double bond right here and a hydrogen here. So the bromine and the hydrogen, we're not going to worry about these yet. We have a carbon here and we have a carbon here. Okay, those are both carbons, right? So if we look at this carbon first, we have a carbon that's attached to a hydrogen, and a carbon. Okay. If we look at this carbon's attached to 1 hydrogen and a carbon through the sigma bond and a carbon through the pi bond. So if you had a triple bond, you'd have 3 carbons there. Okay. So we have 2 carbons and a hydrogen here, 2 hydrogens and 1 carbon here. Which is the higher priority? The one with 2 carbons. So that's going to turn this into, this is going to be 1 for bromine, 2 for this one, and 3 for this one, and 4 for hydrogen. This works with double bonds to oxygen as well. So if you had something like this, here, let me erase. let me just drive you completely crazy. What if we did? No, not that, just methyl group there, and then oxygen, and then hydrogen. All right, let's prioritize these. Okay, so we have oxygen, carbon, carbon, hydrogen. So that means oxygen takes priority. So this is our 1. So that takes us to the next 2, right here. We have this one and this one. Okay, so on this side, we have the carbon with an oxygen for the second one, and a hydrogen. On this side, we have a carbon with an oxygen and a carbon. So which is higher priority, the aldehyde or the ketone? This is the ketone. Yes, the ketone is, because it has a higher priority. The carbon on it attached to it is higher than the hydrogen attached to the aldehyde, and therefore it's going to be higher priority. So that makes this 2, makes this 3, and makes this 4. All right, do we understand that prioritization through double bonds and triple bonds? Okay, the last thing, and again, we don't use it very much, but it's true. If you have isotopes of the same element, so if we had carbon 13, carbon 14, the higher mass element works, but it has to be isotopes, okay? So we have a higher isotope type, and 5 minutes. So we use that rule. It might show up sometime. All right, and we've already done that. And so we're going to assign a couple priorities real quick. And then I'm going to teach you the R and the S rule. Okay, so let's do one more. Chlorine. All right. So, and this is our chiral center right here. So, which is our highest priority? Iodine, bromine, chlorine, or hydrogen? There's a carbon in between the iodine and the carbon center. So this is going to be 1, bromine. So don't get thrown off. You'll have to look at the first bond over to do it by atomic number. This is 2, this is 3 because carbon is 6, and this is 4. Okay, don't get caught up on that. The other thing to do would be something like okay, so obviously the oxygen is going to be 1 and the hydrogen is going to be 4. So now we have these 2 to deal with. So we have this one right here and we have this one right here. So we got a butyl chain and we got an isopropyl. Which one's higher? Right, because this carbon is carbon with a carbon, and a hydrogen. This carbon is a carbon with a carbon, hydrogen, hydrogen. So the isopropyl group has more carbons on it. Therefore, it has more carbons attached to the carbon of interest. And that's why it is higher priority. Okay, so I'm going to go ahead and stop here, and we're going to start assigning R and S on Wednesday after the quiz. We will get up to assigning priority on the quiz. So learn how to assign priority 1 through 4 for the quiz, and all of chapter 4 and up to priority. All of chapter 4 and up to priority. Got it? All right, thank you, everybody. Any questions from there? Okay, so I'm going to go ahead and stop sharing and stop recording.